Okay, here we go, folks, section 4.6. It's on page 198. That's where it's going to start, but if you turn back a page, you'll see the title to this is what? Yeah, Fundamental Theorem of Algebra. Fundamental means foundational, everything's based on it. It's really, really, really important, and it was really important. Happily, it's not that hard. We've actually already been using it in a limited way already. I've told you about it, and you accepted it, ran with it. Here's what the theorem says. I do not like the way the author of the book states it, although it's pretty close. Here's the theorem. Listen, and make sure you're paying 100% attention. We've been studying polynomials, right? You have a pretty good idea what a polynomial is? Think you could recognize it if you saw one? There are powers, different powers of x on each term, right? Only variable we have is x. Those powers have to be whole numbers. Remember? We learned to identify them first section. Okay, so listen and think about all polynomials that you can think of. Oh. Here's what it says. Every polynomial of degree n has n solutions, some of which may be repeated and some of which may be imaginary. But there will be, if it's a fifth degree polynomial, there will be 5 solutions. Okay? Now, are you aware that when there are imaginary solutions, that's what we're going to introduce today, that's what we're going to throw into the mix. Are you aware that when we have imaginary solutions and you graph it, that's the place, it won't hit the x-axis on the imaginary solutions. So if you've got a third degree, think about this, a third degree polynomial, and it goes like this. I guess I'll draw it for you. It starts low and ends high, so it's got a positive leading coefficient. It goes like this and comes around, and before it hits the x-axis again, it takes off and goes up forever. What have you learned from this? There is one real one, and the other two have to be imaginary because it never hits the x-axis more than once. Does that make sense? If it do this as well, it could turn out of the way over here and then eventually hit it like that. But that also means there's one real solution, which means the other two are imaginary. Could start high and end low. I know I'm drawing all these things. Could start like this and then come down. That's one and 2 imaginaries. Could start high, hit here, and then bend out of the way like that. Every one of these is one real and 2 imaginaries for a cube function. Now, do you realize that a cube function could also have all 3 of them be real? See that? Can you have it where there are 2 real? A cubed function with 2 reals?
Yeah.
How can you have 2 reals? Just get 2 of them. How's that?
I want to go through right there, just barely touch it.
Like, so it comes up like this and comes down and just barely snags it right there?
Yeah.
Believe it or not, that's 3 reals, because what do you know about this 0? Multiplicity 2. So there are 1, 2, 3 real ones. It is not possible, folks, in a cubed polynomial, it is not possible to have just 2 reals and 1 imaginary. That's not possible. Here's another reason why it's not possible. This is just graphically speaking. Another reason why it's not possible is because imaginary solutions, when we find them, are produced by the quadratic formula when we have to square root a negative, right? You know what I'm talking about? Let's say that for just a minute that we had a, let's go to the algebra now instead of the graphing of it. Let's say we had a cubed function that factored like this. We had f of x equals x minus 3 was one of its factors because 3 went in the box of synthetic division and it depressed the thing down to a quadratic. Okay, let's pretend that. And that the quadratic result, the quadratic leftovers, was this one. X squared minus 2x plus 10. And so you decided to use the quadratic formula on this. the remaining quadratic. So we know that one of the zeros, when we get down to the bottom, we say x equals. We know that one of the zeros is going to be 3. Right?
Yeah.
Quadratic formula on this, because I don't think of factors. Factors of 10 that add up to 2, I don't think there are any. So I'm going to go to quadratic formula. So it's going to be x equals, for this piece of it, 2 plus or minus the square root of 4 minus 4 times 10 over 2, which is 2 plus or minus. That's 4 minus 40. That's a negative 36 over 2. Yeah?
Yeah.
Which is 2 plus or minus 6i over 2, which is 1 plus or minus 3i. If I take the 2 out. You follow? Do you see how I'm getting 2 imaginaries? Yeah. You will always get 2 imaginaries. If there's one, there's always another. Just like with the ones where this was, if this had turned out this way, that one would have turned out, if I went this direction, I realized that that's what it was before, but if I went this direction, it would be 2 plus or minus. See the 4 in there? See the 4 in there? Square root of 4 is 2, so it's 2 root 11 over 2, which would be 2 plus or minus root 11. These guys also always come in pairs, these types. Why? Because of that plus or minus in the quadratic formula. There's always 2 of them. So if you have a cubed function, a cubed polynomial, 3rd degree, you can't have 2 reals because the third one, I'm sorry, you can't have 2 imaginaries. No, my mistake. Can't have 2 reals and 1 imaginary because the third imaginary, which makes up the third solution, is out there hanging out there all by himself, and he always has a conjugate buddy, plus or minus. You cannot have 2 real solutions and 1 imaginary. So now I want you to think of a 5th degree polynomial with me. Think of a 5th degree polynomial. How many solutions will it have? 5. That's what we just learned. That's the fundamental theorem. 5th degree, 5 solutions. Can it have 2 reals? Just 2 reals? No. Because the other 3 would have to be imaginary, and imaginaries always come in pairs, which means there has to be an even number of them. These 2 would pair up. This one's left out here in the cold all by himself without his conjugate buddy. You cannot have 2 real solutions to a 5th degree. Could you have 1 real on a 5th degree? Could you have 3 reals? Yeah, because the other 2 pair up. Could you have 5 reals? Yeah, it could hit the x-axis 5 times, but it cannot hit it 4 times. Well, it can have 4 real solutions. It could hit it 4 times if one of them's a bouncer, because that provides 5 because it's a repeater, right? But you can't have 4 reals. Could you have no reals? Could they all be imaginary in a 5th degree polynomial? No, because one of them, these 2 buddy up. This guy's left all by himself out there as an imaginary. He can't be by himself. Besides that, you know that a 5th degree polynomial has this sort of behavior. Starts low, ends high. Can you understand? It has to hit that x-axis at least once to get from here to here. It has to. It might hit as many as 5 times. Or 3. Or 1. But not 4. And not 2. Because it leaves the other ones as an odd number. You have to have an even number of imaginary solutions because of the quadratic formula, which always produces them in pairs. Do you follow me? Okay, there's the first concept knocked out. Also, you need to understand, you guys know what synonyms are? What are words that are synonyms? They have the same meaning, virtually the same meaning. They might be slightly different, but they have most of it's the same meaning. We have synonyms in here, and you need to understand that when they ask you to have how many solutions it has or how many zeros it has, it means the same thing. Now, if it asks how many real zeros it has, that's a different question. That's the question I was just asking. How many real zeros does a 5th degree polynomial have? And the answer is 1 or 3 or 5. But if I ask you how many zeros does a fifth degree polynomial have, you always answer 5. Do you understand the difference? So asking how many zeros it has and asking how many solutions it has is asking the same question. Solutions, zeros, synonyms. Real zeros, not a synonym. You clear? Real zeros are x-axis crossings because that's a real number line. All right. So let's look at example 4. Well, look at example 1. This is really, really easy. It's almost insulting to your intelligence at this point. But look at example 1 and read the words carefully. It says, how many solutions does the equation that you're looking at have? 3. How many zeros, B part? How many zeros does the function that you're looking at in B part have? 4, like that. Moving on. Look at example 2. Is it okay that we move on? Is that what's...
Yeah.
All right. Example 2 says, find all the zeros of that fifth degree polynomial. How many can we expect to find? How many imaginaries? 4. 2, 4, or 0. Has to be an even number. 0 is an even number. Did you know that? 0 is an even number. So we may find, in looking for the zeros on this, we may find that there is no imaginaries, 2 imaginaries or 4 imaginaries. Losing my mind. Okay. All right. So let's go after them. If you had this task yesterday on your exercises, or the stuff that you were working on, section 4.5, if you had that task for that fifth degree polynomial, how would you begin?
Well, I got no idea.
You should have, because you were supposed to have done it in section 4.5. You were supposed to find zeros of polynomials in 4.5. How would you begin? Graphing it would be a good way. There's a more efficient way that I just taught you. Polyroot finder. That's where I would begin, because I want to know something that I can put in the box. And if they're all 5 nice and rational and neat, then I just move on. So, I hope you can see this on screen there. We're talking about the fifth degree polynomial in example 2 of page 199, very top of the page. So, we want to go to apps, alpha 8 to get to the P portion, polysomult, polyroot finder, and this is, we're going to go clear over to 5, fifth degree polynomial now. Go to next. Yeah, be careful if you're missing terms. Make sure you build in a 0 for their coefficient. So we got 1. Yes, 1, 0, 1, negative 2, negative 12, negative 8. 1, 0, 1, negative 2, negative 12, negative 8. Oops. Does your screen, do you all have this for your coefficients? And do you see why the 0 for the second one is important? Necessary. Is everybody good? Now, the higher the degree, the longer your calculator has to work to find it. So it may take it a minute. It's worming its way through the solution here. Okay, so what do you notice there? We've got
4 real numbers and 1. Wait, no.
We've got 3 real numbers and 2 imaginaries. Look, it even typed it for you. These are real. And believe it or not, this is negative 1 and this is negative 1. Calculator is experiencing another pixel crisis. But those are 1. I mean, if you got that many zeros behind something, it's suffering a bit. The calculator is. And you must interpret that as negative 1. If you got this many 9s behind something, you must interpret that as rounding up. It's having a little crisis. So what we have for zeros is 2, a negative 1, and a duplicate negative 1. Negative 1 shows up twice, so it's a multiplicity 2. So we have 3 reals and 2 imaginaries, right? Now, let me tell you a little secret about this. Because the imaginaries turned out completely and totally well defined here, that is, wait a minute, I'm thinking differently about this now. Okay. Pay attention to this because you're going to be able to read this. I didn't even notice this until I looked a little harder at those imaginaries. So pay attention. I'll teach you how to read this properly. This E right here, does anybody remember how you pronounce that?
0.
No? Well, yes, it turns out to be 0 altogether, but this is pronounced times 10 to the, remember? This is negative 1.5 times 10 to the negative 13. Guess what that is? Negative point. 12 zeros, and then a 1, 5. And that is
0.
0. This is literally 0 plus 2i and 0 minus 2i. That's what it is. Or in other words, plus or minus 2i. And since that was nice and clean and not irrational, you can just write these solutions down and move on. This is how you would write them. So that you understand what your calculator is telling you and you know how to report them. It's going to be 2, comma, negative 1, multiplicity 2, or in Big Ideas Math, they may ask you to write this twice. For me, this is fine. And then, plus or minus 2i. 1, 2, 3, 4, 5. 2, 3 reals, 2 imaginaries. And this is a bouncer. Yes?
Why for the imaginary solutions just says like
Mine does that too.
Let me show you how you fix that. Either that or I may have to upgrade your operating system on the calculator. We'll see. Go back to coefficient. No, go back to main. And on this one, do you have this here, or is there just a line that says degree? Yeah, now choose polynomial. Just choose that. It should take you to the screen. Yeah, see, your screen doesn't look like mine in the next one. Mine has all that other junk in there. Okay, so let's see if I can turn this on. Let's go and have you calculate report these as well. Really best the eyes instead of just the rules. Okay. So then we save that. We put 5 and 100. So see if we can get her split and solve changes. We have to go further back in. If we have time at the end of this period or before the end of this week, I want you two to come up and I'm going to give you not a different operating system, but I'm going to give you a better app. You can download it. This may still work. We're still going to put this. Now there's that you get.
But mine does something.
There you go. It's got kind of a light screen. Okay. So, how do you suppose this graph of this thing might possibly look, knowing this? If we were going to graph this thing, what do you suppose we ought to put on the graph in order to get some sort of a feel for what this thing might look like? What should we put on here?
A positive 2
A positive 2
and 2 and negative 1.
and negative 1.
That's all.
And what do you notice about, is this thing going to start high and end low, start low and end high, or start high, high and low, low? Which one's it going to do?
start high.
Started low.
You start low because leading coefficient is negative, or positive.
Oh.
You start low and end high. So as it comes up to this, what do you suppose, what's one possibility this could do? As it starts down here and comes up towards these markers on this thing, what's it going to do at negative 1?
Oh, isn't it like the longer the coefficient, like the longer it's going to take to get to the number?
It has to do with even or odd. What's it going to do at negative 1 starting down here? Bounce off. What's it going to do at 2? Go through. Straight through, because it's only multiplicity 1. It could possibly come up, bend down, and go up again, And your two imaginaries are causing this. Right? Could also do this possibly. It might be this. It might at -1 instead, it might bend out of the way like this and then come up and kiss that one and then go through 2. Could do the bending out of the way here. Graph it, see what it looks like. Just graph it. Go back to your home screen, graph it, and see if you can tell. It may not look like either one of those, but those are possibilities. We may not be able to get much detail. We'll see.
Do we need to build any in the graphic?
What's that?
Do we need to build in one for the fourth?
For the 4th?
Yeah.
No. No, you don't. Not when you're graphing. So it did bounce off from below. It's more like this one here, but we can't see this behavior, and it may not even have that behavior. That may not even be what happens. But we know that it's going to bounce off 1, however it encounters it, and we know that it's going to run right straight through 2, and those are the only places it will hit. That's kind of what that indicates. And we don't see the returning behavior here. It just takes off, and that can happen too. But it only hits. It bounces here, it hits up. Okay? Goes right straight through on that. Okay. Complex conjugates. I already talked to you about that. If you know one of the imaginary solutions, you know the other. In other words, if I had told you this list, I said I got a 5th-degree polynomial and here are some zeros, you can be sure that this has got a conjugate buddy. And that one of these is duplicated. Because there's got to be 5. And if 2i is a solution, so is -2i. They always come in conjugate pairs. Conjugate meaning one positive, one negative. A plus bi, a minus bi. Those are always going to come in pairs. That's what the core concept at the bottom of page 199 is telling you. We've already talked about that. So turn a page, and let's take a look at what they're going to have us do in example 3. We've done this before. They're going to give us a list of zeros, or at least some of the zeros, and they're going to make us produce the polynomial they came from. Remember that? No? Shall I take you back to 4.5 and show you where you did this? See if I can remind you what you're doing? Need to? Go back to 4.5, page 195, and look at the problems 41 to 46. See that chunk of exercises? Do you remember what you did on those? You did? Some of you are nodding. They gave you a list of zeros. Sometimes it was an incomplete list because you knew they came in irrational conjugate pairs. And then you used my little trick. Same trick works for imaginary zeros. Really cool. Really cool. So go back to page 200 and look at what they want us to do in example 3, because it's exactly the same thing they wanted you to do in the ones I just reminded you of in the previous exercise. It says, write a polynomial function f of least degree with rational coefficients. That's going to automatically happen. You don't have to worry about that. Whose zeros are 2 and 3 plus I. What degree will this have? Pardon? What degree will this polynomial have if the zeros are 2 and 3 plus I?
3.
How do you know it's 3? Even though they gave you 2, there's 3? Absolutely. That's the thing you got to be aware of. The solutions that they gave you are 2 and 3 plus I. That means this is 1 also. Yeah? Remember that? Come in conjugate pairs? Which means that one of the factors we're going to have to multiply out is going to be x minus 2, just like it was in section 4.5. These two right here were produced by the use of a quadratic formula, right? We need to recover the quadratic that made these for solutions. We do it exactly the same way over here on a piece of scratch paper that we did with the other one. We say x equals, we exploit that equation, x equals 3 plus or minus I. And just like we did when this was an irrational number like root 2 or something, we isolate the ugly stuff. We get rid of the 3 by bringing it over, just like we did that trick with the other one. And just like the other one, squaring is going to clean things up. If you square this, you get x squared minus 6x plus 9. Can y'all do that quickly? This is going to give you, this one you got to be a little bit more careful on. This is not just going to give you I, like, what it's going to give you is I squared.
Which is -1.
Which is -1. Because squaring the plus and squaring the minus just gives you a plus. So squaring this eliminates this. All you have to do is square that part, which is -1 by definition, yeah? Following? So the quadratic is x squared minus 6x plus 10 when you bring that over. See it? Got the quadratic out of those two imaginary pieces? Everybody following or not? Then we FOIL those out. X cubed minus 6x squared plus 10x, and then we distribute that, -2x squared plus 12x minus 20. Clean it up. X cubed minus 8x squared plus 22x minus 20. And if you graph that, it will hit the x-axis in one place at 2, because the other two are imaginary. Follow that? And do you see how similar it is to when we did it when we had conjugate irrationals instead of conjugate imaginaries? See how it works out the same way? The only difference is right here, from here to here, and click in another negative because you're squaring an I. Okay. So that wasn't too bad. Take a look at the monitoring progress on page 200. It's in the middle, kind of lower middle of the page. Page 200, monitoring progress, there are 4 problems there. I want to do number 7 with you to show you that you may end up with irrational reals and also imaginaries in the same problem. So I want you to look at number 7 with me. Let's see if we can walk through that. Similar to what we're doing, what I'm erasing right now, it's very, very much like it, only the zeros, some of them are irrational in radical symbols, and some of them are imaginary. So, in number 7, they tell us the zeros are the square root of 2 and 1 minus 3i. Can you tell me, when we are done with this, the degree of the polynomial we will recover? What will be the degree of the polynomial that we write from these zeros?
3.
Oh, wait, no. 4.
Because this irrational is a positive, but so is his negative buddy because it's irrational. They come in pairs. And this guy right here also has a conjugate buddy. Can you see the 4 solutions?
Yes.
We're going to have to use that little trick on both of these because this is irrational, this is imaginary, and we've used that trick I taught you on both things. So I'm not even ready to write down a couple of factors because these both require the use of my trick. Okay, so I'm going to do this one first, the irrational. So I'm going to say x equals plus or minus root 2. Now normally there would be a number in front here and I would drag it over here so we could square it. But since there isn't, I'm ready to square right now. You see that? And so I have x squared equals 2. If I square that, I get x squared. If I square that, I get just 2, which means that x squared minus 2 produce these two. That quadratic made these 2 solutions. See what I'm doing? Got a quadratic out of these. I'm going to get a quadratic out of these too. I'll pull a little trick over here, a little farther over a piece of scratch paper. X equals 1 plus or minus 3i. This one does have a nice, pretty piece that needs to come over here with the x. X minus 1 equals plus or minus 3i. Square both sides. Squaring that binomial gives me x squared minus 2x plus 1. Squaring this gives me
Positive. Is it negative?
It's -3.
it's negative.
Oh, yeah.
You are squaring the 3 and the I. 3 squared is 9, I squared is -1, the result is -9. Do you see it? Be careful. Don't just focus on this. You sometimes have a number. The last one we didn't. The first example I showed you didn't have a number. But when it has a number, you got to square it too. Squaring this gives you a plus, so you can ignore it. Squaring this gives you 9. Squaring this gives you -1. 1 times -9 is 9. 1 times 9 is -9. So bring that over, and we have x squared minus 2x plus 10. That's the quadratic that produced these. And our task now is to FOIL them together. Here comes your x to the 4th. 4th-degree polynomial, yeah? Minus 2x cubed plus 10x squared. Then we distribute the -2. -2x squared plus 4x minus 20. X to the 4th minus 2x cubed plus 8x squared plus 4x minus 20. 4th-degree polynomial, because there were 4 solutions. This graph will cross the x-axis twice. At a little after 1 and a little before -1. That will be the polynomial recovery on that one. So you have one for the irrationals, one for the imaginary. Same trick. Both produce a quadratic that made those conjugate pairs. Okay, moving on. We're almost done. We are not going to do example 4 because I have never seen an ACT test or an SAT test or an ISAT that has Descartes' rule of signs. That also used to be really, really handy when we didn't have calculators. And now it's obsolete, so I'm not going to teach it to you. I've never seen it on a test that you have to be prepared for. So we're moving on to example 5. Do you know what a tachometer is? Anybody? It's in your car. Yeah, measures revolutions per minute. The higher the tach is up on the higher the number on the tach, the louder the engine, well, not louder, but the higher the engine's revving. Okay? It's how many times the crankshaft is turning over in a minute, right? Revolutions per minute. The crankshaft, as it turns over once, all pistons are fired and pop back down in the cylinder in different sequence. They all fire at different times and moves that cylinder around a little bit, and it does 4,000 RPMs is pretty high, right? But it's not enough to make your engine break. 4,000 times that thing turns over. Every piston fires 4,000 times in a minute. Anyway, that's what a tach is. A tachometer measures the speed in revolutions per minute at which an engine shaft rotates. For a certain boat, the speed, get this straight what these things represent, the speed x in hundreds of RPMs, keep that straight, of the engine shaft, and the speed s in miles per hour across the water, s is moving across the water, x is number of times the engine turns over, are modeled by this. The speed across the water is equal to this 3rd-degree polynomial dealing with RPMs, or the tach rating. They're tied together. How fast the boat goes and how fast the engine's turning over are closely tied. And they're tied this way, in this case. Question asked, what's the tach reading when the boat travels 15 miles an hour? Where does the 15 go? X or S? S. 15 miles an hour is the speed of the boat. So here's what we have. We have I'm not going to go ahead and write the S of X in there. I'm just going to say, I'm going to replace the S with 15. And what's the right side of the equation in terms of X? Read it to me. 0.00. Okay, don't give me the 0 points. Just 0.0. 5 what? 47. X cubed. Okay. Minus 11. Okay. In order to solve this, it has to be equal to 0. That's what all of these things, everything we've been doing, we always set the function equal to 0. So the 15's got to come over. Rather than rewrite this line, I'm just going to subtract 15 from both sides. That'll make a 0 here. And what over here? Yeah, it's gotta come off the constant because it's the only thing I can combine with. So this becomes a negative 26 because we're subtracting 15 from negative 11.
I think that
For the 3.2, it's supposed to be 3.6.
3.62?
Yeah.
Oh, okay. Now everything's good, is that right? So we brought the 15 over and we had created this third degree polynomial equal to 0. Okay, if we graph this, and I'm not saying we should yet, but if we graph this, and let's say it crosses the x-axis 3 times. So it's got 3 real solutions. We expect that because it's a third degree polynomial. That's a possibility. Let's say it hits the negative x-axis twice and the positive x-axis once. How are you going to make the decision? Which one it is if they're all 3 real? Let's say this thing, this is a positive leading coefficient. Let's say the thing graphed like this.
well, you can't have negatives. So you have to-
Negative what? Well, you can't have negative what? For what?
For like because it's not asking, you can't have negative RPMs.
Oh, X represents RPMs. Number of times the engine turns over.
So it has to be positive.
What happens if the boat's going in reverse?
You still are.
The engine's still turning over a positive number of times. So yeah, don't let that fool you. Okay? So if this happened, even though there are 3 real solutions mathematically, there's only one that makes any sense because of what X represents. What happens if it's going to cross 3 times and it crosses the x-axis twice? Like that, the positive x-axis. Which one are you going to choose? Well, you'll have to know something about engines. Perhaps this one is going to blow the engine up. This many RPMs and you choose this one. Or perhaps this one's idling. Maybe this is idle speed and you can't get any speed at all off. 15 miles an hour is not going to come out when the boat's idling. And so you might have to know a little bit more about it. As it turns out, if you graph this, and I assume you can graph it. If you graph it, it turns out it only crosses the x-axis once, and it's positive, hallelujah. So there's no choice to make. Look at the graph that they have there on page 201. I'm assuming that you could make that graph too, by typing in all of these numbers, after you subtract them. And then it crosses the x-axis where you see that little spider marker right there. And if you look down at the bottom of that screen, it is 19.86. So how many times is the thing moving or revolving per minute? This is what we got from the crossing, folks. It crossed only once over here, and it actually went like this. Came up like this and crossed like that, okay? So this thing right here, at the bottom of the screen that we're reading, down here it says x equals 19 point, look at the bottom of that little tiny screen they got for you, 863,247. And over here it has y equals 0, right? What does this mean? What have you found? In the context of the problem, what have you discovered? That it turns over almost 20 times.
No, 100.
120 times?
You gotta times it by 100, right?
Oh, yeah.
So it's 200 times.
It's not 200 times, it's 2,000. It's close to 2,000 RPMs. Because when you multiply by 100, this thing ends up going like that. 2 places over, because 100's got 2 zeros in it. Right? And that's nearly 2,000. So if you had to express what we've discovered here in a sentence in the context of this problem, what would you say?
How like 2,000 RPMs of a revolver.
You about got it, Alexis. Keep going. What'd you say?
That at 2,000 RPMs, the boat and shaft rotates or whatever.
Okay, so it's revving up at 2,000 RPMs, but what does that mean in the context of the whole problem? When the engine's revved at nearly 2,000 RPMs, you're going 15 miles an hour. That's how the type. You got to express both the dependent and independent variable. This is the independent variable. This is just how much the thing's revving. But because it's revving that high, 2,000 RPM, it's going 15 miles an hour. When you express what you have in these kinds of problems, you have to express your sentence with the miles per hour, which is called the dependent variable y, along with the independent variable x, which is your tax reading. You got to make sure you know what you got. Just because you can graph it doesn't mean you know anything about what's going on in the problem. Think about what that graph's telling you. Turn the page and there you go. So you're going to have to write polynomials from given zeros. Make sure you include them all. And you're going to have to find all the given zeros from a polynomial that they give you by graphing and possibly using synthetic division, quadratic formula. Sometimes you'll get imaginaries out of that. For those of you doing it on paper, here's the assignment. Section 4.6 is 1 to 3, 7 to 17, odd, 18 to 21, 23 to 27, odd, 32, 43, 45, 46. 47 is extra credit. That'll add points to your next test if you can do it. Make sure you show all your work, because you don't get credit for just an answer, even if it's correct. So there's extra credit points available if you can do 47 and show all your work. Okay. Quite a bit of time. You got to be able to knock a lot of this out, or at least ask questions about it. Make sure you're working on this, and let me know if I can help you. See you later, everybody. Bye.